We are starting a new unit. We're going to look at our solar system. We're going to look at the planets in our solar system. And before we can begin, I want to let you guys know probably the most important thing that you are going to learn in this entire unit.
How do you pronounce the seventh planet from the sun?
Uranus. Uranus. I was always taught Uranus. Always Uranus. But in America, it's Uranus.
I call it Uranus unless I'm making a joke.
Uranus.
Strictly speaking, it's pronounced Uranus, is the pronunciation. Now, what happened was when the Voyager spacecraft was approaching the seventh planet for its 1986 encounter, the popular pronunciation had become Uranus. And obviously there was the giggle factor, and they didn't want people in press conferences to have to deal with that every single time they said the planet's name, so they decided to change it and make it Uranus.
At least once every night, the Uranus joke comes out of somebody's mouth in the observatory somewhere.
The seventh planet. Oh, Uranus?
Uranus? That's great. You're the first person to say it that way. You're the first person who went there.
Emily was saying that she thinks it would be great to have a probe sent to Uranus for the.
All right, guys, say it with me. Uranus. 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 Okay. Now that we have that out of the way, let's start at the beginning. The formation of our solar system. How did it get here? Not only are we curious about how it got here, but there's a few other questions that kind of naturally would follow from that. What events or materials are necessary to make the solar system? Why are the planets different than each other? And how are they different? And are all planets created equal? Are they all created in the same way? Why do they look different? Etc. Any model of the formation of our solar system is going to have to be able to explain certain observations that we see. Namely, all of the planets are going in the same direction. It's known as prograde. The opposite would be retrograde. So if you're looking at our solar system from above, they're all going in the same direction. Why? If we come up with a model of the formation of our solar system, it has to explain why all of the planets are orbiting in that plane of the ecliptic. Why are they not orbiting in all different planes? Why are they all basically flat in the same plane? Why do we have different types of planets? Why are the inner ones all rocky planets, the outer ones gas giant planets? Why don't we have a gas giant up close, a rocky planet farther away? Why does it look the way that it does? If you want to get more specific, not only are all of the planets going in the same direction, but it's also the same direction that the sun is spinning, as well as the same direction that most of the planets are spinning. There's a couple exceptions. We mentioned that all of the planets are in the same plane, and the planets are basically by themselves out there in their orbit. There's not like two planets in one orbit. So you have a planet, and there's nothing else in that section of space. You have to travel quite a ways to get to the next planet. Why can't you have two planets in the same orbit? Most of the planets' orbits are pretty close to being a perfect circle. None of them are a perfect circle. There are ellipses, and we'll get to that later, but they are pretty close to being a circle. The moons that orbit the planets, almost every single one is going in the same prograde direction that the orbits are orbiting in, that everything is spinning in, the moons spin in that direction. Why is our solar system all going in the same direction? We also need to know why our solar system has so many differences. So the inner versus outer planets. Why is the asteroid belt in between Mars and Jupiter? Why do some planets have moons and others don't? So why are there differences between the planets? Asteroids are very old, but they don't look like a planet. They're much smaller. There's no atmosphere. So why are asteroids, what are they? What the heck is the Kuiper belt and the Oort cloud? We're going to have an entire day looking at these two regions of space. So how did they get there? What are they? And how does our theory of the formation of our solar system explain the Kuiper belt and the Oort cloud? Let's look at what our solar system is first. We mentioned that most of everything is in the sun, 99.8%. I got it right that time. Most of that is hydrogen, most of the rest is helium, and a little tiny bit is everything else. If you add up every single bit of metal, any type of metal, in our entire solar system, it's less than 1%. It's a fifth of 1%. Rock, a little bit more, about 2/5 of 1%. And ice, about 1.5%. And those light gases, hydrogen and helium, is everything else. Because everything is orbiting in the same direction and in the same plane, it seems as though our solar system is not a completely random just jumble of stuff that was flying through space and all just decided to stick together. It seems as though it had a common origin, and that's because everything is going in the same direction. But you also have to try to explain away some of the irregularities. So Venus is actually spinning backwards. Uranus is spinning on its side. Why? Any model that we come up with has to be able to explain that. The model that we've come up with is known as the solar nebular theory. Let's go over it. The nebular theory is the most widely accepted of all how did the solar system get here theories. And it was originally developed by three guys, Swedenborg, Kant, and Laplace. Laplace is the probably most famous astronomer. They came up with this idea to explain how our sun and planets came to be. And it turns out that it's most likely how every single other star and planet system also forms. Here's a quick little overview. You start as a nebula. You clump together. You start to spin, and then you form planets. Let's go over each one of those steps. Number one, formation of a star. How did our star get here? Well, you have a huge, giant gas cloud. How did our star get here? Well, you start out with a whole bunch of material, a whole bunch of gas, mostly hydrogen and helium. Over long periods of time, gravity is going to start to cause that gas cloud to condense, to get tighter and tighter, smaller and smaller, until eventually you get what are known as protostars. What's a protostar? A protostar is where you condense that material enough to where fusion starts to happen. Remember, you have to condense it and get it very hot in order for fusion to start. As soon as fusion turns on, it's going to be known as a protostar. Why is it not a regular star? Because there are still material that's being added to it. It's not done growing. A protostar is a star because it's doing fusion. It's giving off heat and light and energy, but it's not done growing. There's still more material that it's drawing in, and it's getting bigger and bigger. In order for a star like our sun to completely grow to its full size and stop growing, to get out of the proto stage, anywhere between 10 and about 50 million years. What originally caused that big cloud of gas up in the sky to just start condensing? Well, we don't know. Nobody was there. Could have been a couple things. Maybe a nearby already formed star passed and it just disturbed the gas cloud and they started to condense. Maybe it was a supernova shockwave. Supernova we'll get to when we talk about the death of stars, but it's a big explosion that sends out a shockwave in all directions, and if that shockwave goes into a big cloud of gas and dust, it might start to compress it. Once you start to compress it, gravity is going to take over and do the rest. Why do we think that? Well, we can see a big cloud of gas and dust, and then boom, there's a supernova. This supernova is going to send out a shockwave into all of this surrounding material, all of that surrounding gas, and it's going to start to compress that. That could be the beginnings of brand new stars. We've actually got some pictures of this happening. So if you zoom in enough, you can actually start to see little tiny glowing dots inside of this cleared out area within a giant gas cloud. Here is a protostar that's doing Here is a protostar that is doing fusion. You can see that it's glowing, and it has cleared out all of the material in that little blank area, has fallen into that star within this giant cloud of gas and dust. So we have photographs of this actually happening. Now that we have a protostar within this big cloud of gas and dust, what happens next? Well, it turns out that when you form a star like this, you now get this big protoplanetary disk that forms around these little baby stars. Why does that happen? Because as anything starts to collapse, anything in the universe is going to collapse, is going to start to spin. Think of a figure skater on ice. When a figure skater pulls their arms in, they start to spin faster and faster. And as this gas cloud gets pulled in, it's going to start to spin faster and faster. And that's why our sun is rotating. As it's spinning, all of this material that it is pulling in is also going to start to spin. That's why planets are orbiting in that direction. As you spin something, what happens to it? It starts to flatten out. Think of somebody making a pizza dough. And if you throw the pizza up in the air, it's going to flatten out. So if you start collapsing, you're going to start to spin. And the faster you spin, you're going to start to flatten out. Well, that explains a whole bunch of stuff. It explains why everything is going in the same direction. It also explains why everything is in a flat ecliptic plane. Two of the biggest questions were just answered for us. Way to go, planetary nebular model. We actually have photos of this happening. Nobody was around to see it happen with our solar system, but we can see it happening elsewhere. In order to see that something is flat, you have to be looking at it from the edge. If you look at it from the top, you can't tell that it's flat. So we have photographs of these big molecular gas clouds that have been flattened out. You can see that there's actually a glowing star in the center. We can't see it. It's being blocked by this edge of the disk. But we can see these flat protoplanetary disks that are surrounding these stars. So we know this happens because it happens elsewhere in the universe. It makes perfect sense that it also happened in our solar system. Now we've got a star, and we have this, what's known as a protoplanetary disk, a bunch of material that is just spinning around this little baby star. Some of that material is still falling in, causing the star to get bigger and bigger, but not all of it falls in. Some of it's actually spinning, orbiting too fast for it to fall in, and it just continues to orbit. And what we are now going to call this protoplanetary disk is an accretion disk. What does accrete mean? It means to slowly accumulate over a period of time. If you watch this little video clip closely, you will see that some of these pieces of material slowly start to accrete. Slowly, they start to come together to make a bigger piece of material. We start forming the inner terrestrial rocky planets. Inner planets are rocky and they start coalescing and getting bigger and bigger and bigger. If the accretion disk is big enough, you also have these rocks in the outer areas of our solar system that start to accrete, start to get bigger and bigger and bigger. Eventually, you're going to get to things that are about the size of the moon, of Theia. We would call these planetesimals. Why are they not full-grown planets? Because they're still adding more material. They're not full-grown yet. Once they are full-grown and there's no more material to add, then they're known as planets. But while they are getting bigger and bigger, you're known as a planetesimal, even though you're still growing. Those planetesimals can form actually pretty quickly in less than 500,000 years because there's so much material. However, to get a full planet where it's actually accumulated everything that's in its little area can take 100, 200, 300 million years, maybe longer. So to get a planetesimal, which is almost planet size, is very fast. But to have that planet stop growing, to have it have collected all of the material that it possibly can until it's used all that material up, that can take a very, very long time. These planetesimals are going to smash into one another. And you're going to have these giant planet-sized objects smashing into other giant planet-sized objects. We've actually already talked about that happening in our solar system with Earth and Theia, which is how the moon was formed. And we've got photographs of this happening. So we have these little protostars that are condensing all of that gas. And this protostar has a little planet that's already formed, and we can actually see that planet. It's so hot that we can see it glowing. It's molten. So we have photographs of little baby planets orbiting around little baby stars. Now this coalescing is almost all the solid material. Things like rock, things like metal, which is why the inner planets are made up of mostly rock and metal. The gases that would be surrounding this planet, those gases actually get blown outwards because a very young star is going to have a very active solar wind. And that solar wind is actually going to push those lighter hydrogen and helium gases outwards towards the outer parts of the solar system. There's not a lot of gas left over to accumulate in the inner solar system. Most of that gas is then pushed outwards to the outer solar system. When I say outer solar system, I'm talking about past what's known as the snow line. The snow line is we're far enough away from the star that you can start to have things freeze. If you're too close, most of the time ice cannot form. You're too close to that heat source. You move far enough away and you can start to have ice formed, hence the name snow line. You can start using things like frozen methane, frozen water, frozen ammonia to start building your planets. You're not relying just on rock and metal anymore. You're now able to use rock and metal as well as frozen gases like ammonia or methane. Now that you have all of this extra material, all of this frozen water, frozen methane, frozen ammonia, all of these things that can now solidify because you're far enough away from the sun, now your planets are going to get extra big. Ice that these substances are forming actually stick together better than rock. So these giant planets with all of this material far out from the sun actually form very, very fast. And as all of that hydrogen and helium is blown outwards from the solar wind, these giant planet cores that are out farther from the sun start to collect all of that gas with their gravity. While Earth was forming close in as a rocky planet, Jupiter also has a little bit of rock at the core, a little bit of ice at the core, and that got to be a pretty large core actually, and all of that gas that was blown outwards by the solar wind, Jupiter was now big enough to gather up most of that gas. That's why Jupiter is the biggest planet. Then as you go farther out, Saturn gathered up the second most, whatever was left over. You go a little bit farther out, and now you have Uranus and Neptune, which would have gotten bigger had there been more material. The problem is that Jupiter and Saturn gobbled up most of that extra gas, and not as much made it out to where Uranus and Neptune were. That's why they're not as big. So you have the inner rocky planets, which are mostly made out of rock and metal, because those things solidify at higher temperatures than gas does. And then the gas was blown outwards till you had these giant planet cores, because there's rock and metal, as well as frozen ice that are making bigger planet cores. All this gas just gravitationally sticks to these giant planet cores, forming our gas giants that we have in our solar system. So far, we've been able to explain why everything is spinning and orbiting in the same direction, because that big cloud of gas and dust just started spinning as it was condensing. We've been able to explain why things are in a single plane, because as something spins, it flattens out. We're even able to explain why Venus is going the other direction and Uranus is on its side, because as they were forming, they were being hit by other planetesimals, things that were virtually the same size as them. And if you're hit hard enough, you're going to change the direction that you're spinning. We've also been able to explain why the inner planets are small and rocky, because they use mostly rock and metal to form, and most of the material was blown farther out to those gas giants. Those outer planets were able to use things like snow and ice to get bigger and bigger cores, and then able to gather up much more of that hydrogen and helium that was being blown out by the solar wind. We've explained quite a bit of what we see happening in our solar system by this nebular theory. Here's all of it put together in a nice little clip.
Our solar system is the region of space which falls within the gravitational influence of our sun. The solar system is thought to have begun forming about 5 billion years ago from a giant spinning cloud of gas and dust. The core of this cloud grew under the influence of gravity and became became denser and hotter. As material fell towards the growing core, the cloud increased in speed and flattened into a giant spinning disk. Eventually, the increasing temperature generated enough energy to trigger nuclear fusion. This fusion marked the birth of our sun. The lighter gas was swept far out into the solar system, leaving heavier, rockier material and metallics with high melting points nearer the sun. Molten metal and dust particles stuck together to form clusters, which in turn stuck together to form rocks. Mutual gravity caused these rocks to come together, eventually to form planets. In the hot inner regions of the solar system, rocky planets with metal cores were formed. In the colder outer regions, things were different. Further from the sun, temperatures dropped. Water vapor condensed and turned to ice. This ice, combined with the vast amounts of gas blown away from the sun, meant there was a lot more material here than in the inner regions. As huge cores of ice and metal grew, the gases swept away at the sun's birth were attracted through gravity. When the accretion of most of the ice and gas was complete, we were left with the gas giants. The solar system as we know it is around 4.6 billion years old. It's looking pretty good for its age.
There's more out there, though. It's not just planets. We got moons, comets, asteroids, dwarf planets, Pluto. We have the Kuiper Belt and the Oort cloud. All that's coming up in the next week or so. And the last thing that I have for you guys is a little activity that walks you through what temperature you need to be in order to form different types of planets. You'll find this on Canvas.